Hello, in this video I will talk about Cascade controllers. Well, first I'll tell you why we use Cascade controllers. In control engineering, the schemes are designed in order to determine the behavior of certain systems and provide a reaction to external and unexpected inputs that mitigates the disturbances on the system's performance, thus assuring an optimal process. The more complex a system is, the more accurate the control scheme must be. Cascade control is mainly used to achieve fast rejection of disturbance before it propagates to other parts of the plant. It is also used for processes with slow dynamics such as temperature, level, humidity, and others. Cascade control can be applied in a useful way to any process in which a measurable secondary variable directly influences the main controlled variable. Cascade control is a variety of single-loop PID or PI control arrangement in which two or more controllers are connected one side on the other of one loop, in such a way that the disturbance is minimized by feeding the output of the first one to the following one as a set point. This configuration allows the disturbances to be attended simultaneously at different points of the plant. It is important to note that the response of the second controller has to be faster than the outer one, thus assuring that it rejects a disturbance before its effect passed onto the next component. This preventive control monitoring allows a faster and more accurate control to a known disturbance, though in practice it raises costs significantly. Now I will show you an example for you to understand more about this concept. The objective of the control scheme in this heat exchanger is to control the process fluid temperature. In a common control scheme, a simple feedback control would be designed for this system, but in this case, we will analyze the cascade control scheme. Instead of feeding the output of the PI temperature controller directly to the control valve, it is fed as a set point to a feedback PI-based steam flow controller. This second loop is responsible for ensuring the flow rate of the steam does not change due to uncontrollable factors, such as the steam pressure changes or valve problems. In order to understand this, let's consider that the heat exchanger is in a steady state operation. The outlet temperature matches the set point and the controller output is constant. A sudden increase in the steam pressure will cause steam flow rate to ramp up. This will cause a gradual change in the controlled variable. Without the flow control loop, it will not take corrective action until the outlet temperature is already affected. By implementing the cascade strategy, the feedback flow control loop will adjust the valve position immediately when the steam flow rate has changed to bring the flow back to the value of the previous steady state condition, because the flow set point given by the temperature controller didn't change as the outlet temperature did not yet change, preventing a change in the outlet temperature before it happens. Note that the flow control loop must be tuned to run much faster than the temperature control loop, therefore cancelling the effect of the flow variance before it affects the process fluid outlet temperature. So then, in order to analyze, we need to consider that the heater system can be modeled by the diagram shown, that the transfer function of the plants have been already determined, and that the inner loop controller C2 has already been designed. In consequence, we need to just design the outer controller. Firstly, we implement the blocks inside the red rectangle in MATLAB. In this way, we will be considering this part of the system as a new plant and subject it to a step experiment in order to observe its response. Once implemented the system and inserted a unitary step input, the simulation is run, and as we can see, a response similar to a first-order system is obtained, which means we can fit the first-order model to the response. In order to do this, it is just necessary to obtain the final value, as well as the time in which the response is 63.2% of the final value. This is the definition of the time constant tau. Once tau was read from the cursor measurement, we are just missing the gain in order to determine the first order transfer function. This is determined from the division of the final value over the input step, which is, in this case, was unitary. This operation is derived from the final value theorem, but in this time I will not explain it. With these parameters, the fitted model for the inner loop was obtained. The next step is to validate that the first-order system is a good approximation of the new plant. This is done by adding the obtained transfer function to the scope of the previous implementation, using the same step as the one of the previous analysis. The simulation is run, and as it can be seen, this was a correct approach. Now, in order to design the outer controller C1, the fitted model is implemented as shown in the figure below. Notice that once again, the proposed controller is a PI, which will be implemented as shown next. Now, the parameters kc1 and tau I1 are calculated by proposing an operation point. In this case, we will look for a controller so that the closed-loop system has poles in -1 divided by tau 2. This can be done by substituting the transfer function into the characteristic equation and then leaving it to a simplified form, and also by obtaining the polynomial of the poles. Then we can match these terms and obtain the parameters of the controller. Finally, the controller is implemented in Simulink and compared with a single-loop PID controller. This was done by considering the leftmost disturbance to occur at 40 seconds and having a negative value of -20, while the rightmost occurs at 30 seconds with a value of 10. Note that the set point is 100 degrees. Ignoring the fact that the PID controller in blue was not designed to behave like the Cascade controller response in yellow, the Cascade controller has a better response to disturbances as it mitigates its effects. This response shows the principal reason of existence of the Cascade controllers. It allows for disturbances to be attended simultaneously at different points in the plant, while achieving a fast rejection of disturbance before it propagates to the other parts of the plant. That's all. Thank you for your attention.